Welcome to our presentation. We're Modec Technologies and we're in group number 7. The group members are Irwin Reyes, Luis Garcia, Rick Sanchez, and myself, Melanie Ramirez. So basically the team wanted to help in some way the army, and we were reading that 22% of the soldiers go through a mental condition. And well, most of the times these conflicts are caused due to elevated blood pressure, dehydration, or when they are in chemical exposures. And these conflicts are caused due to changing temperatures or when they have physical and physiological issues. A little bit of background of our project is that the soldiers go through two types of stresses. One, it's the combat operational stress, and basically this stress is caused by seeing an injury or by having a personal injury. And if this stress is not treated correctly, it's gonna be changed to PTSD. One way to find out the stress in a person is by the HRV or the heart rate variability, since it helps us to monitor sleep issues, cognitive process, stress, and basically overall health. And our team is gonna be measuring the stress by using an ECG sensor that it's gonna help us to monitor the heart rate variability.
So for the problem statement of our project, Plisky, who is a doctor and assistant professor at a sports resident program at the University of Evansville, he basically stated that when you mix psychological factors with physical actions, you may encounter some problems and might be prone to injury or other bad things that might happen. For the goal statement, we basically want to prevent musculoskeletal injuries and monitor the stress of a person throughout different stages, whether they're stressed or whether they're in combat or whether they're not in combat or whether they're just sleeping. Basically, we're trying to prevent any psychological and musculoskeletal injuries by monitoring the stress and try to prevent any risks from happening.
Okay, so for market analysis, this is our position on the market. It will be on the high quality and the high durability. Comparing it to the other products, our product it will be the orange bond to the right. Even though there's so many products right now, the actually competitors will be the Hexoskin and the Cospo from China. This is because they use the heart rate variability, and this is the best way to calculate stress right now.
So based on a survey that we applied to the ROTC members, we created our QFD, which has our customer requirements and our functional requirements. So by creating the QFD, we know that our product is gonna be lightweight, it's gonna be wearable, it's gonna be manufactured with a durable material, and it's gonna be comfortable and with a high quality.
Okay, for our conceptual design, going from left to right, our first design, we wanted a monitor and heart rate sensor on the forearm, and then an Arduino and the battery on the top part of the shoulder. On the second design, we wanted a similar design, but with the monitor on the forearm, but this time we have the heart rate sensor on the upper part of the bicep. On our third design at the very right, we wanted to make sort of vest that held the heart rate sensor and the controller and battery pack. For our final prototype, we ended up going with this design, which was the first design, which was the monitor and controller on the upper part of the forearm.
On the final design, we actually try to make it as the most comfortable as possible. We did this using TPU material, so it'll be flexible and so it'll be lightweight for the soldiers to use. Also, we did the screen a little bit larger so that the soldier's name could be so that you could see the whole soldier name on it with the respective stress status. We also put these little holes on the top and the bottom so you can put the strap so you can put it on your arm as a prototype, but this time it will be way smaller, lightweight, and it will last to 8 hours.
For FMEA, which is the failure mode and effects analysis, which helps calculate what part on the product has a higher chance to fail, We're prioritized by a risk priority number, an RPN. The prototype to the final design had a lot of improvements, which made for an overall much lower risk priority, so less failures overall.
Our team decided to manufacture a product based on TPU, which is a thermoplastic. And some of the advantages of this material is that it has high abrasion resistance. It is also resistant to changes in temperature. It's also excellent resistant to oil, grease, or water. And it's also really flexible.
For the electrical components for our final design, we will be using LCD or an OLED display. This is because this is the most current use right now screens, and to be more specific, we'll be using a Gorilla Glass that Samsung is doing right now because it has the more durability right now. They don't tend to crack that easily, and that's what we need in order for our product to last the most possible in order to check our soldier stress. We also will be using a CR2025 battery that right now it can power up a 3-volt device like nothing, and it can last in our project to an estimate of 8 hours. And of course we will be using the ECG sensor, and this is because using the ECG sensor we can actually get a heart rate variability that give us a value of how stressed is the soldier.
For our manufacturing process, we chose to do injection molding since we're doing mass production. And the machine that we chose is a height injection molding machine. This machine cost approximately $49,000, and we chose this machine since the clamp capacity that we need for our part is 125 tons. The process sequence that we're gonna have, first we're gonna be receiving the material, then we're gonna change that material to the injection molding area, and we're gonna be manufacturing the part. After we have that, we're gonna change it to the electrical encoding area so we can place all the electrical components. And after a part is done, we're gonna change it to the quality control part. If the part passes that area, the quality, we're gonna be putting the part or the product in the package, and then we're gonna change it to the shipping area.
For the facility layout of our project, we first identified the sequence that we just recently stated in manufacturing process. And with the sequence, we are able to justify the importance of each section of our facility by doing an activity relationship chart. With that, we are able to put that data into block plan. By placing it into block plan, we're able to run several simulations of facility layouts. And this was not the best one with the score, but it did correlate more with our sequence based on how our process from our product occurred. And of course, there's HR, which is human resources, offices, tooling, injection molding is IM, electrical. Electrical would also be the assembly. That's where we're going to put both of them together. And then 6 would be coding, 7 is quality, 8 is packaging for our product, RS is receiving and shipping, and the 10 is the restrooms. And we also, those are not the only restrooms we're going to have. We're going to try to put some restrooms between 2 and 1 for the offices and HR, because sometimes you might need someone hiring a person or when the person needs to go to the restroom. That way we have 2 on different sides of the facility.
For our facility location, as you can see to the right, the green states are states that have the highest active duty personnel, and the dotted states are states where we decided to put the manufacturing plants. We ran a demand allocation model using Excel's What's Best tool and found the cheapest cost for transportation and new plant setups. So we ended up going with these 5 states here, and they were the cheapest for transportation per year, coming in at 4.4 million, and the most expensive combination of states was 7.5 million per year. For future demand of the first year, there are 1.3 million active duty personnel in the U.S. and 800,000 reserve troops in the U.S. We figured 30% of active duty troops would be ordering, and maybe 30% of reserve troops would be ordering. So per month, we're looking at about 32,500 to 52,500 units per month. We used moving averages of 4 weeks and exponential smoothing, giving us an average demand per month of 38,000 to 41,000 units per month.
For the economical analysis, we first tried to do the time measurement of our product. We then did the return of investment, payback period, depreciation value, internal rate of return, and the net present value. For the time measurement, we basically took how long it would take for us to do a batch of 100 parts, and then we got for how many parts we can do per year. So per year, we got that we can do a total parts of 552,000, but that's without discarding scrap parts on every single. So we would do roughly 500,000. For the section of return of investment, depreciation value, and payback period, the total yearly cost was calculated with different types of costs like property tax per year, cost of shipping, cost of making and slash packaging, the worker cost, the engineering cost, the manager, like the manager that runs the whole plant, the energy, the machines, the maintenance, the cost of screens, because we're gonna have a supplier of screens. And we also got the coding cost, the equipment cost, the facility cost. All of those were researched. Um, Also, the total profit for us was 106 million, roughly 106,897,013 dollars, and our return of investment was 54%. We also calculated the depreciation value, which was $20 of every year. That is 10% of our what the product is, and that way we got it for 10 years. That way we can see when's the best time for us to either um, put another product in the market or update it and send updates. We also did the payback period. The payback period was roughly about 2 years, 1.9 years with no depreciation, and with the discounted payback period, it was roughly 2.2 years. And we can see the cash flow here on the right side, how we had negative numbers for the first 2 years, and then we were able to make profit after that. And after that, we did the internal rate of return and the net present value. These values are fixed because these values of 106 million, that's how much we would make per year if we had a fixed cost as a no depreciation value. And that's how we calculated the internal rate of return of 40%. As we can see, we have an IRR per year here on the right side. We also have negative numbers, negative 51%, negative 4%, and then we start to increase. And we did it over 10 years just to keep it the same. And we also, the first year was the investment, which was 197,202,000, and the net present value, we also calculated it, which was 236 million, and that would be the present value after the year.
For future recommendations, we would like to increase the amount of features and health monitor systems in the device. If possible, we would like to make this device waterproof and also move the market from soldiers to whatever person that needs some help with stress or something, and we hope we could use it on hospitals too. As a conclusion, we hope to reduce the amount of injuries, decrease the amount of money the military spends on them, and analyze the data for combat analysis or the well-being of the soldier. This is the end of our presentation. Thank you.